Have you ever wondered why fighter jets seem to explode into a sonic boom as they hit high speeds? Or how fighter jets feel as they punch through that sonic barrier? Today, we're diving into the intense physics of supersonic flight, discovering why sonic booms occur, the challenges that come with speeds over Mach 1, and how new tech might bring back commercial supersonic travel. So, get ready as we break down what really happens when jets tear through the sky at speeds faster than sound. To understand why breaking the sound barrier is such a milestone, we first have to understand what sound actually is. Sound isn't a force or substance. It's a vibration that travels away from a source in the form of waves. These vibrations travel across mediums such as air, water, or metal. In air, these sound waves are able to travel through a series of pushes and pulls among air molecules, known as pressure waves, which pass energy from one molecule to the next. This vibration forms a repeating pattern, regions of higher pressure with air molecules packed closer together, followed by regions of lower pressure with air molecules further spread apart. The greater the difference in between these pressure areas, like the higher the pressure is here and the lower the pressure is here, right? The more intensity. It's important to keep in mind that sound comes in the form of waves, and because of that, it's defined by characteristics of waves, such as intensity, amplitude, and frequency. The intensity of a sound wave, which is what we commonly refer to as loudness, depends on the wave's amplitude, or height. The greater the amplitude, the louder the sound. This amplitude is determined by the difference in pressure. The higher the high pressure and the lower the low pressure, the louder the sound, because it has a greater amplitude. It being the sound wave, of course. So, when jets reach supersonic speeds, the buildup of pressure releases a shockwave. That shockwave brings about significant pressure, and combined with the normal air pressure that you have all around you, the high air pressure coming from the shockwave creates a large amplitude, and that large amplitude creates an intense sound wave, which in turn creates a loud boom. If you want a video diving deeper into what sound actually is, let me know in the comments. Now that we have a better understanding of what sound actually is, hopefully, let's talk about the sound barrier. Similar to how sound isn't an actual force or anything, the sound barrier isn't like a physical obstacle, right? It's just a term used by pilots since the 1940s as it pushed aircrafts closer to Mach 1. In those days, many believed it was impossible to go past Mach 1. As engines would fail, control surfaces would stop working, and the structural stress from going at Mach 1 would start tearing planes apart entirely. Essentially, the sound barrier wasn't an actual wall, but rather an unseen phenomenon of physics that defied the materials and engineering of the time. When planes approach the speed of sound, they start encountering intense air pressure in front, causing severe drag and vibrations. When jets reach supersonic speeds, they produce a shockwave that can be heard on the ground as a loud boom. But why does it boom instead of just getting louder? Think of it this way. When a jet flies below Mach 1, the sound waves it produces can be spread out ahead, right? That allows the people to hear it coming from a distance. At supersonic speeds, however, the fighter jet goes faster than the sound waves it generates, compressing them into a more powerful shockwave. Once the shockwave reaches listeners on the ground, they hear it as a sudden, intense noise, the sonic boom. The sonic boom trails the fighter jet throughout its entire path, so long as it's over Mach 1. So anyone standing under it in what's known as a boom carpet hears a sonic boom when the shockwave reaches them. However, the pilot never hears anything. They're flying too fast for the sound to catch up to them. The pressure waves that form sound trail the fighter jet. Also, it's not a single sonic boom. There's always two. One whenever the shockwave reaches you, and another one when regular air pressure replaces the higher air pressure from the shockwave. As of right now, I'm preparing a future video talking more about supersonic aerodynamics, so let me know if you guys would be interested. However, let's talk more about the challenges of supersonic flight now. While supersonic flight has tremendous advantages, the sonic boom poses a huge drawback, especially over populated areas. The iconic Concorde, a commercial supersonic jet, was banned from overland flights in many countries because of its disruptive noise, relegating it to transatlantic flights only. The loud boom it produced could be heard up to 25 miles away, making supersonic travel inconvenient for communities living under flight paths. This problem remains a major barrier to commercial supersonic travel today. Moreover, supersonic flight suffers from drag and fuel inefficiency. Going past Mach 1, these jets start experiencing much more drag than subsonic planes, especially in the speed known as the drag diversion's Mach number. This speed value, which sits at just around Mach 1, causes significant drag spikes due to shockwaves, which then lead to fuel inefficiency. Many supersonic jets tend to avoid flying between Mach 1 and 1.6, as it costs a lot more fuel with minimal benefits in speed. For this reason, many commercial jets fly just below Mach 1, somewhere around between Mach 0.7 and Mach 0.8. Pushing beyond this threshold could cost 4 times the amount of fuel per passenger for the same flight length. Despite these challenges, technology is constantly evolving at spectacular rates, making the future of supersonic travel more practical and accessible than ever. To finish the video, let's talk about the future of supersonic flight, the very near future. NASA's X-59 project is designed to reduce the sonic boom to a quieter thump rather than a very disruptive sonic boom. Through innovative design, it's set to reshape the pressure waves that form shockwaves, creating a quiet supersonic jet. If successful, the X-59 could prove that commercial supersonic travel doesn't have to be loud, opening up new possibilities for travel over land. Companies like Boom Supersonic are also working on the next generation of passenger supersonic aircraft. Their Overture jet aims to provide sustainable, quieter, and more efficient supersonic travel. Designed for Mach 1.7 speed capabilities, this jet will sit 64 to 80 passengers for a range of just about 4,250 nautical miles, and be introduced by the year 2029. With technology improving and demand for air travel also increasing, Boom's efforts could bring back supersonic travel to the commercial world within the next decade. Supersonic flight remains one of the world's greatest achievements, and while we've come a long way since the days of the Bell X-1, the challenges of speed and sound continue to push engineers and scientists. With advancements in noise reduction, fuel efficiency, and aerodynamics, the future of supersonic travel could soon be quieter, faster, and more accessible than ever. So, next time you hear a sonic boom, remember, it's not just a noise. It's the sound that marks one of the most remarkable achievements in human history. Now that you know a little bit more about how our world works, why don't you check out this video that YouTube thinks you'll love.